के बिना कर दूं क्या?
नहीं नहीं रुक, आ गया। हाँ कर
हाँ
सकते हैं
ठीक
वैसे।
है आराम से। हाँ मतलब ज्यादा लोग दे आएंगे भी नहीं मेरे हिसाब से तो।
कोई नहीं
हम्म।
तो
आने वाला है।
एक अभी तो इतना रुक लिए तो दे ही दे फिर अभी।
हाँ। अभी तो
चल रहा है
कौन
क्या?
साइट बीच में क्रैश हुई थी क्या?
मैंने तो नहीं किया नोटिस, मैं तो इवन ही कर रहा था। ओ हो गया,
अच्छा।
चल हो गया।
हेलो।
अभी तो
चल रहा है
कौन
क्या?
साइट बीच में
हेलो।
क्रैश हुई थी क्या?
हाँ हेलो हेलो। ये
जो कॉटलन हीरोज क्या है?
वो हम बेसिकली कॉटलिन ओनली कॉन्टेस्ट होता है वो। एक ही लैंग्वेज में कोड
हाँ
करना है, जिसको कॉटलिन की प्रैक्टिस करना है उसके लिए है
ओ ओके ओके।
इसका प्रैक्टिस राउंड भी चल रहा था ना दो
हम्म।
तीन दिन
वो।
पहले।
तक
देख रहा हूँ।
कॉटलिन नहीं दिया, आता ही नहीं वो।
रशम देखो, डिस्कॉर्ड पे मैसेज किया।
ओ ठीक है ठीक है।
यस। डाला प्रशम?
हाँ हाँ डाल ही रहा हूँ थोड़ा वेरीफाई करते हुए रुक एक मिनट।
ओके।
हाँ डाल रहा हूँ।
क्योंकि स्ट्रीम चालू हो गया।
ब्रो 5 minutes more then start।
क्या? हेलो।
हेलो।
स्टार्ट करता हूँ भाई, छोड़ो। एक डाउट है किसी को?
मैं
ये हो गया होगा, डिस्कस कर लेते हैं। ये क्या था? Maple has two positive integers a and b. She may perform the following operations any number of times to make a equal to b. And the operation is that she can choose any positive integer x and multiply either a or b by x. Her task is to determine the minimum number of operations required to make a equal to b. Okay, it can be proven that this is always possible. So test cases. Yeah, in the first test case, you can just multiply a by 2 and they will be equal in just one operation. In the second test case, You can multiply A by 300 to get this, and multiply B by 3000 to get something else. So basically, we can always turn this into the LCM of these two values. Okay, so we just have to check. So there are only three conditions here. Either A and B are already equal, in which case the answer is 0 because we don't need any operations to make them equal. Uh, or either A is divisible by B or B is divisible by A, in which case it would require us only one operation to make them both equal. And the third test case is that A is not divisible by B and B is not divisible by A, in which case we will require two operations. We can just turn them into their LCMs and the answer will be 2. That's all I did in my code. A equals B, the answer is 0. If any of them is divisible by the other, then answer is 1 or the answer is 2. Okay, let's move on to B. So what is given in B? Maple wants to bake some cakes for chocolate and vanilla. One day she discovers in magical cake ovens, the ith oven bakes AI cakes per second. The cakes remain in their respective ovens until they are collected. At the end of each second, she can teleport to any oven and collect the cakes which are in that oven. Our task is to determine the maximum number of cakes Maple can collect in m seconds. Okay, so I'll just dry run this test case. Okay, so in this test case, there are 3 ovens and we have 4 seconds. Okay, so what will happen in those 4 seconds to all of these ovens? We can simulate that. So in the first second, in the first second, uh, the first oven will have one cake, second will have two, third will have three. In the second, this will have two, this will have four, this will have six. In the third second, this will have three, this will have six, this will have nine, and in the fourth second, this will have four, this will have eight, and this will have 12. Okay, so one thing to notice here is that it would always be profitable to pick the cake which has the maximum value in the very end. Like we can always pick 12 in the fourth second, and we can ensure that this 3 does not get compromised. Similarly, in the second before that, we can always pick this, and in the second before that, we can always pick this. This would be the most profitable operations. And the first test case, in this case, the first second doesn't matter because we will always be collecting, even if we collect 1, 2, or 3 here, we will always be collecting it after that in second, third, or fourth test case. Right. So it doesn't matter whether we choose this, whether we perform this first operation or not. Basically, even if we had 3 seconds in this, the answer would have been the same as it is right now when we have 4 seconds. So yeah, that's all I'm doing. We can always just pick this element, the last element. So I took the input and I sorted it in the reverse order so that because we always have to pick 3 first, and we will pick 3 min of n comma uh, time number of times. So yeah, so the operations is m. We will always pick it this number of times, the operation number of times. Operation is basically this m. Yeah, and we will just keep adding it. And now we have one less operation for the second last case, which is why I did ops minus minus here. And I just output the answer. Any doubts in B?
No.
Cool. Okay. So see, in this case, in this question, we were given 2 people. Each of them are given 2 raised to the power k number of cakes. Okay. And Chocola and Vanilla now have to redistribute the cakes such that Chocola ends up with exactly x cakes and Vanilla gets the remaining cakes. Yeah. And in each step, what happens is the person gives half of his or her cake to the other person. And our task is to determine the minimum number of steps required to reach the target distribution. So let's say for this test case, we are given 2 integers k and x. In this case, k is 2, x is 3. So k equals 2 here. So let's call the 2 people A and B. Currently, both of them have 2 raised to the power 2 cakes, which is 4. So both of them have 4 cakes right now. And we need to find out how many operations are required so that in the final step, A has 3 cakes and B has the remaining cakes, which is 5. Okay, so how can we calculate this? So what can happen in this case? Uh, let's dry run this test case 4 and 4. Yeah, A and B. So in the first case, A can, since we need to reduce A, we can give half of A's cake to B. So this will be 2 and this will be 6, right? But this will not proceed further. So we can think of we can think of redistributing B's cake. So this B can give 2 cakes to A. This becomes 6, this becomes 2. Then A gives 3 cakes to B, and this becomes 3 and 5 is our target. And it took us 2 operations for this. Alright. So how do we stimulate this situation? How do we simulate the situation? So let's say for this case, 4 comma 4, that is A is initially 4, A has initially 4 cakes, B also has 4 cakes. So there can be 2 cases, either A gives 2 cakes to B or B gives 2 cakes to A. So it could either become 2 comma 6 in one case, one operation, or it could become 6 comma 2. If A gives its cake, then it becomes 2 comma 6. B gives its cake, then it becomes 6 comma 2. Okay. Now there can again be 2 cases here. Either A gives half of its cake to B, so the A becomes 1 and B becomes 6 plus 1, which is 7, or B gives, this is A, or B gives half of his cake to A. So this becomes 5, comma 3. Here also there are two cases. Either A gives half of his cake to B, then this becomes 3, comma 5, or B gives half of his cake to A. So this becomes 7, comma 1. Now, one thing to notice here is each value is achievable. Basically, if each value from 1 to 4 is achievable. A initially has 4 cakes, and we can always make A any value from 1 to 4, right? So it is always possible to perform these operations. It is, I think, also given in the question. It can be proven that under the given constraints, a valid solution always exists. Yeah. So we have to find, in this case, how many operations does it take to make A 3, right? So where is A 3 here in this case, right? So we have to find how many operations it requires to come here. So we can easily see via this tree that it takes only 2 operations to get here. So how do we simulate this situation more? So one thing to notice is that when we backtrack, when we go from this case to this case, so when do we basically get this case from here? When A gives half of his cake to B, right? So if we backtrack this, we can give A 3 cakes and B, we can subtract 3 cakes from B. Basically, we can double A, or we can double B here. In this case, B gets doubled, right? So what we have to notice is this problem just simplifies to making 3, 5 equal to 4, 4, which means both the cakes are same, which is the initial state that we have. So that was the key point here, to backtrack, right? Now one thing to notice here is that since A is less here, the parent of this will always have A greater, and since B is less here, the parent will always have greater B. Like in this case, B gets doubled, and in this case, A gets doubled. Similarly, in this case, in this case. So whatever is given to us, let's take some other test case. 3, 7. Yeah. So 3, 7. So K is 3. So A and B both have 8 cakes initially. And we want A to have 7 cakes. So how many cakes do we want B to have? We want 16, which is the total number of cakes, minus 7, 9 cakes. So we want this state, 7, 9. So what we can basically do here is, since A is lesser in this case, we can just double A and we can subtract 7 from B, right? So this becomes 14, 2, and we can keep doing this operation until both A and B become equal, basically until we reach the initial state, and we can just count the number of operations. That's it. Yeah, so I just assigned the cakes to A and B. This is basically 2 raised to the power k plus 1, which is the total number of cakes, and I assigned the required cakes. A requires x cakes in the final state, and B will obviously require first, which is this total number of cakes minus x. So until A and B do not become equal, that is until we don't reach the initial state, I am just backtracking this state, x comma total minus x state. Whenever A is lesser than B, I am just doubling A and I am subtracting A from B. And this is the operation titled 1 because we are operating on A. So I'm just pushing back 1 in the operations vector. And in the end, I'm just printing these operations, but in the reverse order because we are backtracking and we need it to be reversed. Yeah. Any doubts in C?
No.
Cool. Okay. So in this question, Maple is given a rooted tree consisting of n vertices from 1 to n, where the root is always 1, indexed 1. Each vertex of the tree is labeled either 0 or 1. Uh, Maple forgot how the vertices are labeled and only remembers that there are exactly k zeros and n minus k ones. For each vertex, we define the name of the vertex as the binary string formed by concatenating the labels of the vertex from the root to the vertex. More formally, this. Okay. Yeah. So basically, we are just given a tree and we want to assign either 0 or 1 to each of its nodes. Alright, I'll just make this tree. Okay, it's already given. Okay. So this is the tree given to us in the first test case. What we are supposed to find is to determine, we have to find the maximum beauty among all labelings of the tree. So beauty of a tree is defined as the length of the longest common subsequence, LCS, of the names of all the leaves. Okay, so in this tree there are 4 leaves, 4, 5, 6 and 7. And we have, how many zeros do we have? We have 3 zeros. So we have 3 zeros, and which means we have 4 ones because ones are always n minus the number of zeros and n is 7 here. So we have to assign this 0 and 1 to this tree such that the longest common length of the longest common subsequence from the root to the leaves is maximized. Okay, so in this case, how can we assign the zeros and ones? So we have 4 ones, right? So we can just assign 0 here, 0 here, 0 here, 1 here, 1, 1 and 1 here, right? So now the length of the longest common subsequence is 3 because till each leaf the pattern the path that we traverse is 0, 0, 1 from root till the leaf. So the answer is 3 here. Yeah. Let's take the second test case as well. In this case, we have 2 zeros, which means we have 7 minus 2, which is 5 ones. So we have 2 zeros and 5 ones. And we need to assign these to this so that the length of the LCS is maximized. So now one thing to notice here is that the answer can never be greater than 2 in this case, because the path from root to leaf in this case and this case is only 2, even though it is 3 here. It is only 2 till here, so the length can at max be just 2. Okay, yeah. So we have to notice this first, that we need to now focus on maximizing. We need to focus on assigning only till this level, because these don't matter. Because at max, even if we get a same path from here to here and here to here, this and this will always have a path of size 2. So only this much part is relevant for now. Okay. So now we have to assign 5 ones here and 2 zeros here. So we can just assign 1, 1, 1, 1 here. And we can just assign a 1 or a 0. We can assign anything here. And now the path is same from here to here and here to here. And we can just assign anything here. Since 0 is assigned here, we can assign 0 and 1 here, right? But the answer will always be 2 here, because this is same. Okay. So the first thing to notice here is that we will have to calculate the depth of each node. So the depth of this node, 0 based indexing, it will be 1. Depth of these nodes will be this will be 0, my bad, and this will be 1. This will be 2. And then we need to notice that we need to find the leaf with the minimum node, minimum depth. So 6 and 7 will have minimum depth here, which will be 1. And we are only concerned with all the nodes having depth less than or equal to 1. Okay, so only this is our tree which we are concerned with. And now we need to allocate these zeros and ones to these nodes, so that for each level it only either has all zeros or all ones. Each node has the value all zeros or all ones. Okay. So yeah, the first thing to do is just calculate the depth. Yeah, I just took the input for the tree here, and yeah, this calculates my depth and it stores it in the level vector using DFS. Okay. And here I calculate the minimum length of the depth for each leaf. So whenever the size of the adjacency list for a particular node is 1, which means that it is a leaf, then I'm just updating my mini, which stores the length of the smallest depth for any leaf. Okay. Okay, now next, what we can do is, so now our problem essentially narrows down to just allocating this 2 and 5, just allocating this zeros and ones to only this tree, right? So what we can do here is, we can notice that we can always traverse from the lower left depth. So in this case, we can further simplify this to just storing the number of nodes till this depth, which is the minimum depth for a leaf node. So the vector will store 1 and 4 here. This is basically the level 0 has only one node and level 1 has 4 nodes. But we are only concerned with the number of nodes for a level. So we can essentially just store this in a vector. And now our problem is just that we need to allocate uh, how many zeros were there? Yeah, 2 zeros and 5 ones to this vector, such that all of these four should either have 0 or 1, and all of the elements should basically have just 0 or just 1, right? So here we obviously can't put two zeros here because all the four should be same. So we will have to put four ones out of this here, and then we can just put anything here and it works. Okay. Now, in case there is one more element, let's say there is one more depth of 4 here. Basically, if there are two more nodes here, basically, we will essentially get this vector, and we still have just, uh, let's say we only have two zeros and two 5 ones, which won't be possible because we have more number of elements. But still, let's say this is the case, and this is the vector. So we could, okay, this will never be possible though. But yeah, still the answer will be these two elements because we will always put this here and this or the one here. So basically we can just reverse sort this vector and we can just put whichever is minimum. Like for example, if there are four zeros and five ones here, we will always choose the four zeros to be put here. Because if we put the five ones here, one will remain and it will cause problems in the future. In case we have like one more level here which has two nodes, then this will cause a problem here. So yeah, that's my approach. Here I created that vector which has the number of nodes per level, and I just reverse sorted the vector, and this is the number of zeros is k, which is given in the problem. Number of ones is n minus k, and if both zeros and ones are possible to be put in that level, then I put whichever is minimum. If 0 is minimum, I remove the zeros and I do answer plus plus. Answer is basically the LCS size, longest LCS size we can obtain. Or I just subtract it from 1 and I do answer plus plus. If only zeros are greater than v of I, then only zeros or only ones. And yeah, that's it. Any doubts, any?
Did you prove that reverse sort thing that you did in contest or like intuition based?
No, no, no. Like it is always provable. Uh, let's take any vector. Let's say 2, 3, and 4. How many zeros should I take? Let's say there are, okay, let's say there are 6 zeros and 3 ones. Okay. So, yeah, so the one thing to notice is since it is a tree, level I will always have greater than or equal to number of nodes than the nodes in level of I minus 1, right? Because each node will have at least one child unless it is the final node like this thing. But we are calculating this leaf, right? I mean the leaf which has the maximum number of maximum depth. Sorry, minimum depth. Yeah. So we are only concerned with this tree currently. once we calculate the leaf with minimum depth, we can always say that level of I, the number of nodes in level of I is always greater than equal to number of nodes in level of I minus 1. So the vector will always be something like this. And whenever we reverse sort this, so this becomes 4, 3, 2. We can allocate either 6 here or 3 here. But we cannot allocate 3 here because 3 is lesser. So 6 will work. Let me take a better test case. Let's take 3 here and let's take 4 here. Now in this case, yeah, so in this case we will always have to take the 0 here, because if we take this 1 here, we won't be able to allocate here. Let me erase this. Yeah, so this is the vector which is formed, and if we allocate ones here, if we allocate, this is zeros, right? If we allocate zeros here, then yeah, this is done. But we have the number of zeros remaining as 2 and number of ones remaining as 4. Now we won't be able to allocate zeros here. So we will have to allocate the ones here. And now zeros is just 2 and ones reduced to 1. Now we won't be able to allocate both of these here. Right. Therefore, it is always profitable that whenever we can allocate both of these here, we will always choose the minimum number. So we will allocate 1 here and then 0 will always satisfy this, and we can put 3 zeros here, 3 zeros here. If we do this in ascending, I did it in ascending in my first code, then let's take the same example, I guess. 3, 3, 4. Number of zeros is 6 and number of ones is 4. Now we can't follow the same approach in the ascending order here because we will allocate the ones here, right? So 1 will become 1, 0 will be 6. This gets satisfied. Here we will have to allocate the 0, 0 becomes 3, ones is still 1. Now we cannot allocate this to here because this should either have all zeros or all ones. So reversing will always work.
Can you try this case?
Yeah. Which one?
Six, 6 zeros, 5 ones,
Okay. 0 is 6, ones is 5.
and 4, 3, 2, 2.
Array is 4, 3,
3, 2, 2.
2, 2. Okay. So we will allocate ones here. Wait, 6. Does this add? Yeah, it does. Okay. So we will allocate ones here. 1 will become 1. Zeros will remain 6. And yeah, this is not required. This is done. Now we allocate zeros here. Zeros will become 3. 1 will become 1. Now we allocate zeros here. Zeros will become 1. And 1 will also be 1.
But we can do 4 plus 2, 6, and 3 plus 2, 5.
4 plus 2, 6. And 3 plus 2, 5. Hmm. Yeah, we can actually. Okay. Then this might get hacked or system test will fail. Yeah, this might get hacked in this case.
I think
Um,
weak test case. That's why 1000 plus submits.
yeah, possible. Even E2 got accepted though. Can we form a tree like this though? Like the first, this element will always be one, right? The last element, the root node. Yeah, even that can be formed. Can a tree be formed like this? Like, I think it won't be possible. Mm, what if we take 4, 3, 2, 2, 1? Yeah, this will fail too. No, this won't fail actually. Yeah, the first element is always 1, so I don't think there would be a case like that.
I think there would be some like maths proof that if one exists, then we can do the greedy.
Yeah, yeah, quite possible. Because of this one, everything is getting accepted. Alright, that was it for this PCD. Bye bye.